Diffusion is currently at the core of video and image generation, but now things are changing and it's coming for text as well. Now, traditionally, people have relied on autoregressive models for language generation because language is sequential in nature. However, this next token prediction has some real drawbacks. It's both compute and memory bound, and the reason is that it has to look back at all the previous tokens that it has generated. But now this is changing because diffusion is taking over text. In diffusion, we replace the sequential generation with parallel generation. Now, it's not very similar to simply adding noise the way you do it in images, but the end result is parallel generations block by block. Now, there have been a lot of approaches where people have trained diffusion models for text from scratch. However, I'm seeing a very interesting new approach where they're combining autoregressive models with diffusion. So this is 2Tower from Nemotron, a new diffusion language model. They're claiming 2.4 times faster. But if you think about diffusion model, speed is the main thing people use it for. So that is not really interesting. What is interesting is that half of this network never trains. It's basically a frozen solid, and that freeze is the whole trick NVIDIA is using. So they took an autoregressive model they already had, cloned it into two different towers, froze one, and taught the other to fill in blanks. Now, this fill in the blanks part is the most important part, and that's how diffusion works for text, because it swaps noise for masking. I'm going to come back to that later in the video, because this is a lot of people confused about text diffusion. Okay, so let's have a deeper dive into this model. So on Hugging Face so far, they have released only the base model. We don't have the Instruct RL or chat tuned version yet. Now, text diffusion is really hot right now. We have seen models from Inception, from Google Gemini, and even a diffusion Gemma. So NVIDIA is not the first one here. But the main thing is that how exactly did they build this model? Because that is very different from what we have seen before. So they took a Nemotron 3 nano model, cloned that exact model. Now each tower runs 52 layers. The architecture is exactly the same in both cases, with combination of Mamba 2, self-attention, and MOE. Now the MOE part uses 6 expert out of the 128 per token, plus a shared one. So each tower only activates about 3 billion parameters. So we are looking at a total of about 60 billion total parameters, which means you need a couple of H100s to run this in full precision. Now, the interesting thing is, does this ablation throws away performance or not? And that is actually the interesting piece here. Okay, so on aggregate, it's able to preserve 98.7% quality of the original autoregressive model. But I think the aggregates are not important here. The main thing is, if you look at individual benchmarks, this is where things gets really interesting. So if you look at things like general knowledge, it holds up really well. Multilingual actually goes 3 point, which is kind of curious. But code drops about 2 points and math drops 3 points here. So using this architecture actually has its own cost. And this is where you would actually expect it. Because for things like math and code, if you get the single token wrong in parallel generation, that is going to impact the performance. Now, this approach solves one of the biggest problems that diffusion models have. One network is doing two jobs at once, representing the clean text you already have and denoising the mess you are generating. Now, the paper phrase is that those two jobs pull the same weights in different directions. And as a result, both of them gets worse. It's like asking a person to deliver a keynote and be their own simultaneous interpreter. So NVIDIA splits the work across two specialists, and these are the two towers that we saw. The speaker keeps giving the talk. That's basically the context tower. Now, here's the interesting thing, that it reads the prompt and everything is generated strictly left to right, as an autoregressive model would. And it never gets trained. It's basically frozen in time. Now, the interpreter in the booth is the denoiser. which is the same starting checkpoint, but fully retrained for a different way of producing text. Okay, so the question is how these two towers actually talk to each other. And this is kind of my favorite detail in this paper. So earlier designs mostly passed along one thing, which was basically the final hidden state or a summary off of the top of the context network. Now, a two tower connects them layer by layer. So say in the denoiser, layer 1 is going to cross attend into layer 1 in the context layer, and so on. So picture two identical towers with a sky bridge on every floor instead of one cable between the rooftops. Now it works because both of them started identical, right? So every layer that is communicating with every other layer is speaking the same language. The denoiser also gets a little ADA-LN timer. This is an idea from image diffusion that tells how corrupted the current block is. Now this adds additional 1.5 million parameters, which is nothing compared to the 60 billion parameters of the network. Okay, so this brings us to the generation itself, which is very different than how images are generated. So in this case, the denoiser doesn't just predict one token. It gets handed a block of 16 slots, every one a mask token. Then it basically loops predict all 16 positions at once in parallel, and then commit every position where confidence clears a certain threshold. In the next iteration, it remasks everything it wasn't sure about and runs again, where the committed tokens are now sitting there as anchors. So a really good example of this is the game of Sudoku. Where you don't fill the grid cell by cell from top left. You fill the cells you are certain of, and every number you lock in narrows what fits around it. All right, so how does this work in this two-tower approach? So once a block is fully clean, the frozen tower reads it, updates the cache, and a fresh block of 16 masks appear. Now, the autoregressive model is doing one token per pass, but the diffusion model is doing generation in blocks. Okay, you can actually watch this in their published traces. The commits pile up in the first few steps of each block. Now, the interesting thing is that the model is free to commit in any order, but the order forms an almost perfect left-right triangle. Now, which is really interesting given the architecture where you have 23 of the 52 layers are basically Mamba, and only 6 are attention. So this left to right instincts actually kind of make sense. Now, one thing you should be thinking about is that if these are the copies of exact same model, are we seeing any new capabilities? And the thing is, there are actually none, right? So the denoiser was trained with 2.1 trillion tokens, which is a fraction of 25 trillion tokens that was used for the original Nemotron nano model. So this essentially is simply a decoding conversion, not a smarter model. And they did some ablation studies. They tried just continuing to train the backbone the normal way. It got worse. So they were seeing about minus 10% in general knowledge and minus 17.8% on math. They also tried tying the towers, one shared set of weights, doing both jobs. Again, it was basically a disaster. Minus 26 on general tasks and worse across the rest. Now, based on their ablation studies, this freezing of the network actually made more sense. But it also has its own cost. So it gives you a speed up. However, you're going to have two 30 billion weights sitting resident in the memory the whole time. But only the frozen tower carries cache across sequence. So memory grows with length like a normal autoregressive. Now, in the paper, they also point out to something really interesting, which shows that this model is brittle in certain situations. So the release checkpoint is trained for a block of 16. If you sample it to 64, just changing a single setting, they saw that the generation collapses completely. For example, the human evolve dropped from 76 to almost 20%. and GSM 8K to 2.2%, which is kind of crazy. We're not talking about 22, but 2.2. But they also found that MMLU, which is multiple choice, barely moves at 78%. So the knowledge is there. It's basically the generation process itself that shatters. And it's very sensitive to the parameters or configuration that you're using. Now, they found that if you go lower than 16, the performance remains there, but it's a lot slower. Now, keep in mind, this is a base model. They have plans for releasing the post-trained versions. So we're going to have to wait for that in order to actually test the model's capability. Okay, so this is actually a pretty exciting and novel new architecture. We'll have to see when we have the instruct and RL version of the model. But NVIDIA is really pushing these novel and exotic architectures when it comes to models. For example, Nemotron in itself is a hybrid of Mumbai and Transformer. I haven't seen many other companies experimenting with new ideas. Maybe the DeepSeeks of the world are a good example of Chinese companies doing a lot of innovation. Anyways, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.